Hi, I'm Suyash Mehra, a PhD student at the University of California, San Diego, and I'll present our work on write predictions for persistent memory systems. This work was done during my internship at the University of Virginia. I'll start with a high-level summary of our work. Persistent memory, or PM, is a non-volatile and byte-addressable memory. The motivation for write prediction is that PM programs need to explicitly order their stores to ensure recoverability. Moreover, PM applications need to perform additional operations like encryption, integrity verification, and deduplication. Both store ordering and PM support operations result in a slowdown of persistent memory applications. To mitigate these additional overheads, we introduced PM Weaver. PM Weaver predicts PM stores and hides the external latency by pre-computing the PM support operations. PM Weaver does provide a software-transparent way of predicting PM writes. On average, PM Weaver offers a 1.63 times performance improvement of the baseline system. Next, I will go over some of the background information on persistent memory programming. Persistent memory is a class of memory that allows byte addressability like DRAM, small access latency compared to disk, and low cost per gigabyte compared to DRAM. Persistent memory is a non-volatile memory and can be used as crash-consistent storage. Persistent memory is commercially available in DIMM format as the Intel's Optane DC persistent memory module. Next, I'll explain some of the fundamentals of persistent memory programming. Crash consistency requires an application to be explicitly order its stores. Another characteristics of PM applications is that they have to order and flush these stores frequently to maintain crash consistency. Next, I'll explain persistent memory programming with an example. There's a crash-consistent persistent memory function that inserts a new node to the head of the list. The first step that this function performs is to allocate a new node in the persistent memory using PMAlloc function. It also assigns the correct values to the field of this new node. Next, to make sure that the application can recover the old head of the list and a crash, creates a backup with the value of the current head and marks the backup as valid. The function then makes sure that the backup has been stored in the persistent memory and will not be lost on a power failure by issuing a persist barrier. Once the backup is valid, the application updates the head, persists it with a persist barrier. Finally, since the head is crash consistent, the backup is marked as invalid. Crash consistency requires the programmer to do frequent and ordered write-backs, slowing down the execution. Next, we'll look at the timeline of a PM write-back. Here are the structures that a PM write-back passes through. In Intel's ADR-based processors, the processor and the cache are volatile. That is, they lose data on a power failure. But the memory controller and the PM are in the persistent domain. Any data that reaches the memory controller will be flushed to the persistent memory on a power failure using capacitors. To understand how stores move through these structures, we'll look at an instruction trace. First instruction, store A, is a store that writes to the value in cache. Similarly, two more instructions, store B and store C, write part of the same cache line. Once the data on the cache is modified, the program executes a persist barrier. Persist barrier, as explained earlier, writes back the cache line to the memory controller. Now the data is in the memory controller, it is persistent. But in a power failure, the data still has to be flushed to the PM from the memory controller using its on-chip capacitors. Now that we know how data moves to the persistent memory, we can look at the latency of these operations. Each PM write-back that the program issues has the following latency profile. First, the write is issued from the core. The write takes a small number of cycles to reach the cache. After that, the processor issues a persist barrier, which flushes the data from the cache to the memory controller. Next, once the memory controller queue is full, the data is written to the persistent memory media, which takes the longest amount of time. Once this is complete, the execution continues. PM programs also require additional operations of the data written to the persistent memory. These operations include encryption, integrity verification, and deduplication. Using these operations further adds to the critical path latency of write-back. However, pre-computing these PM support operations can take them off the critical path. Thus, predicting PM writebacks would allow us to pre-compute these PM support operations. This concludes the background and motivation for the need to predict PM writebacks. Next, I'll explain the challenges and observations in doing so. Now that we know that predicting PM writebacks can improve system performance, we'll look at the two main challenges in predicting PM writebacks. First, How can we predict PM writebacks using existing information available during execution? Second, once we know how to predict a PM writeback, when should the predictor trigger that prediction? To begin, we'll look at how we can predict a PM writeback. The first observation we make is that the address and data of a PM writeback is often carried by PM stores. To understand this in more detail, I'll explain the execution of a simple PM function that updates a persistent memory location. Function update takes as input two arguments, location to update and the new data. As we've seen earlier in PM programming examples, the function first creates a backup of the current data. Next, the function updates location and issues a persist barrier. Finally, validates the backup. To understand how to predict the writeback of line 6, we'll look at the instruction trace of this function. The first argument to the function that carries the location of the update corresponds to store 5, while the second argument to the function that carries the data for the update corresponds to store 3. The writeback corresponds to store 8 in the instruction trace. It's now easy to see that store 3 contributes to the address of the writeback, while store 5 contributes to the data of the writeback. It shows that the store instructions of a persistent memory program can predict the address and data of a future PM writeback. Now that we know that store instruction in a program can predict future PM writebacks, we have to design a mechanism to trigger these predictions. To understand how to trigger a prediction, I'll first explain a simple PM example that uses transaction. PM transactions are provided by libraries such as Intel's PMTK that allows programmer to perform a sequence of operations that appears atomic with respect to crash consistency. In this example, the function listInsertHead uses a transaction to insert a new head to the linked list. In the first step, it calls a transactional allocator txNew to allocate a new node and initializes its field. Next, it backs up the next field of the current head using txAdd and updates it to the new node. Since the semantics provided by the library internally issues a persist barrier, there's no need to explicitly issue one. Next, the function backs up the current head and updates it to the new node, completes the transaction. One solution to trigger a prediction would be to use the first contributing store instruction. However, just one instruction can result in various predictions, as we'll see in the following example. In the first example, we have a listInsert data function that takes a string as an input, processes it, and inserts it into the list using a transaction. Next, the function listInsertEmpty also inserts a new node to the list but does not take any argument as input. Both the functions, however, allocate a new node highlighted in blue and issues a PM writeback. In both the functions, the node allocation call, that is txNew, is the first contributing store for the prediction. Without a naive trigger, the predictor would have no way of telling the two predictions apart, thus resulting in false sharing of the trigger. However, we observe that predictions are unique to context. To capture the context, we use the sequence of stores leading to the first contributing store. In the example from last slide, we see that listInsert data has unique context before its first contributing store. Call this context as the store's PC path. PC path is calculated by XORing the PCs of last n stores leading to the first store of the prediction. Now that we know how to predict PM writebacks, I'll introduce PM Weaver, a mechanism to predict PM writebacks in the hardware. Here's a brief overview of PM Weaver. PM Weaver works in 3 stages. The first stage is the learner, which learns the relationship between the store instructions and PM writebacks. The second stage is the predictor, which combines the data from the learned combination of store instructions to predict a PM writeback. The final stage, or the validator, resolves the mispredictions when the real writeback is issued by the processor. To better understand the working of the learner, predictor, and the validator, we'll use an example to demonstrate the process. The learner identifies the relationship between the store instructions and PM writebacks. I'll start with an execution trace of a simple PM program. The program starts by executing a store with PC1. Observing the store, PM Weaver adds to the store history buffer, a structure that keeps record of recent store instructions. Similar to the first store, the processor executes several stores that all get recorded in the store history buffer. PC4 and PC5 write to the persistent memory that is highlighted in gray. After executing store at PC5, the processor issues a writeback. The learner, on observing this writeback, looks through the store history buffer to find previous store that can predict its address and data. In this example, the learner observes that the write-next data can be predicted by a store with PC1 and store with PC2. Similarly, the address can be predicted using the store with PC3. The learner, on observing this relationship, adds a new entry to the predictor table. Predictor table is a structure that the learner uses to notify the predictor of new relationships. The first entry inserted to the predictor table is of the store with PC1, which predicts the upper half of the right bank's data. The next entry, that is PC2, predicts the lower half of the right bank's data. Finally, the entry PC3 predicts the right bank's address. The learner also records the PC path associated with the first contributing store, in this case 5, which captures the context of the first store. The context is later used to trigger the prediction. This entry is then used to predict future PM writebacks by the predictor using corresponding store instructions. Next, we'll look at the predictor. In the next step, the predictor uses learned relationships to predict PM writebacks using store instructions. To demonstrate this, we'll continue with the execution of our simple PM program that executes the same instruction but with new data. First, the program executes store with PC1. On its execution, the predictor calculates the PC path, which is 5. Since the predictor has an entry with the same trigger, we'll trigger a new prediction. Wait for the rest of the contributing store. The predictor also uses the source data to construct the prediction. In this case, we'll use PC1's data to predict the lower half of writebank's data. Next, the program executes store instruction with PC2, in which the predictor checks if it can contribute to any of the pending predictions. In this case, the predictor uses source data to predict the upper half of writebank's data. Similarly, when PC3 executes, the predictor uses the source data to predict the writebank's address. Once these steps are completed, writeback prediction is ready and will be sent for validation. Next, we'll look at the validator. One step in PM Weaver is to validate predictions before the PM state is updated. This is done when the processor generates an actual writeback for the corresponding prediction. The prediction generated earlier is stored in a structure called prediction result buffer in the memory controller. When the writeback is issued, the predictor compares the address and data of the writeback to that of the prediction and updates the PM state. In case the writeback was a misprediction, it is also discarded and the PM support operations are recomputed. Next, we will look at the evaluation of PM Weaver. We evaluate PM Weaver using a modified version Gen 5. The workloads include low-level and transactional workloads from Intel's PMTK Fireworks. For the evaluation, we use two different sets of PM support operations: encryption and integrity verification, and deduplication. First, we'll look at the performance improvement using PM Weaver. The y-axis represents the normalized execution time to a system with no PM support operations. The light-colored bars represent the execution time of the corresponding PM support operation, while the dark-colored bars represent the execution time with PM Weaver. As we can see across both encryption plus integrity verification and deduplication, PM Weaver improves performance by a significant margin. On average across the workloads, PM Weaver provides a 1.63 times improvement for encryption plus integrity verification and 1.26 times improvement for deduplication. Next, we'll look at the prediction coverage of PM Weaver. Prediction coverage is the number of unique PM writebacks that PM Weaver can predict. We show two separate prediction coverage, one for the address of the writeback, while the other for the data. Across all PM workloads, see that PM Weaver can predict the addresses of a significant number of writebacks. However, prediction coverage for writebacks data is lower, shown with the shaded bars. This is because predicting data correctly, PM Weaver has to predict all 64 bytes of the data, compared to just 8 bytes for the address. Overall, PM Weaver covers addresses of 81%, while data of 50% of the all writebacks. Thus, PM Weaver is effective in predicting data and address of majority of the writebacks. In conclusion, PM applications need a software-transparent way to hide the latency of PM writes, PM support operation. We observed that predicting PM writebacks and pre-computing their results allows us to take the extra latency off the critical path. To do this, we propose PM Weaver, a mechanism that predicts future PM writebacks using past stores. PM Weaver provides a 1.63 times speedup for encryption and integrity verification, 1.26 times speedup for deduplication. PM Weaver provides a software-transparent solution that requires no changes to the ISA or source code of the PM application. Thank you.